there is string theory.
Famous physicist Brian Cox has finally revealed new evidence about the origin of the universe that has left everyone shocked.
The new evidence is this young lady who, in University of Yorkshire or something, where was she? And she made a remarkable discovery very recently, the last couple of years ago, of this huge ring in the sky of very, very distant galaxies which form this beautiful circular ring. And another one, which is a big arc, and she showed me it's probably really a circle too, not quite the same center, this ring and this arc. And now she's found a third one. So what are these huge rings doing? Where do they come from? They're so big that there's no time for anything within the standard model of cosmology. They'd have to be right in, well, before the Big Bang. And that is not what people think. There shouldn't be a before the Big Bang. But then I said, ha, that's nice, because my theory says there was a big before the Big Bang.
Have you ever looked up at the night sky and wondered what was there before any of this existed? Before the stars, before the galaxies, before the very first atom ever formed, what was there? For decades, scientists told us the Big Bang was the beginning, the absolute starting point of everything. But what if that's not the whole story? What if the Big Bang wasn't the beginning at all, but simply a transition, a moment of transformation from something that came before?
The closer and closer you go back into the Big Bang, the less important the mass of particles become. They're effectively massless for a completely different reason. And so they're massless at the Big Bang, they're massless in the remote future. So the key idea is that both ends, you don't have any mass. And so therefore the geometry is the geometry of conformal.
Recent discoveries are challenging everything we thought we knew about the origins of our universe. Keep watching as we uncover what Brian Cox and other leading physicists are now revealing about the universe's true beginnings and the astonishing evidence that may rewrite cosmology forever. Let's start with what we actually know. The standard story of the universe's origins goes something like this. About 13.8 billion years ago, everything that exists was compressed into an incredibly hot, incredibly dense state, a single point containing all the matter and energy that would eventually become everything we see around us. This was the Big Bang, and for a long time that was considered the beginning. Nothing came before it. Time itself started at that moment. But here's where things get interesting. The modern version of this story includes something called cosmic inflation, and inflation changes everything. According to current cosmology, before the hot dense phase we call the Big Bang, the universe underwent a period of breathtakingly rapid expansion. We're talking about a growth spurt that makes anything else in nature look like a crawl. Imagine starting with a universe smaller than a single atom, smaller than the nucleus of an atom, and then watching it double in size and double again and keep doubling. How many times? At least 80 times. In less than a millionth of a second. The numbers are almost impossible to grasp, but the math is clear. By the time inflation ended, that tiny piece of space had grown larger than the entire observable universe we see today. All 350 billion galaxies and everything in them. All of it emerged from a patch of space so small it would be invisible to the naked eye. Here's the question that keeps physicists up at night. What started inflation? What stopped it? And perhaps most importantly, how long did it go on for? The answer to all three questions is the same. We don't really know. We have theories, of course. The leading idea is that inflation was driven by a mysterious form of energy that permeated empty space itself. This energy had a strange property. It exerted a kind of negative pressure that pushed space apart, causing it to expand exponentially. Think of it like this. Ordinary matter and energy pull things together through gravity. This mysterious energy pushed things apart. And it pushed so hard that it stretched the fabric of space itself to unimaginable scales. But here's the thing. We don't know where that energy came from. We don't know why it existed. And we don't know why it eventually stopped. Some theories suggest that inflation doesn't stop all at once. Instead, it stops in patches, like a pot of water boiling in different places at different times. Every time a patch stops inflating, that patch becomes a universe, a bubble of normal space and time floating in an endless sea of inflating space. This idea is called eternal inflation. And if it's correct, it means our universe might not be the only one. There might be an infinite number of universes being produced all the time, everywhere, forever. Brian Cox puts it plainly. Inflation tells us that the period of time before the Big Bang was extremely cold and empty, but that empty space carried enough energy to stretch the universe to enormous size. That's not speculation, that's mainstream cosmology. But what came before inflation? That's where things get truly mysterious. This is the question that has haunted physicists for generations. What was there before the Big Bang? If time itself began at that moment, then asking what came before is meaningless, like asking what's north of the North Pole. But many scientists, including some of the most respected minds in physics, believe that the question is not meaningless at all. One of those scientists is Sir Roger Penrose, a Nobel Prize-winning physicist who has spent decades developing a radical alternative to the standard picture. Penrose doesn't believe the Big Bang was the beginning. He believes it was a transition, a moment when one phase of the universe ended and another began. Here's his argument in simple terms. According to Einstein's theory of general relativity, space and time are described by something called the metric, a set of numbers that define the geometry of the universe at every point. The metric has 10 components. 9 of those components describe the shape of light cones, the paths that light can travel through space and time. But the 10th component is different. It describes the scale of the universe, how big things are. Now here's the key insight. Scale depends on mass. Without mass, you don't have scale. And there are 2 places in the universe's history where mass effectively disappears. The first is the remote future. As the universe expands forever, stars burn out, galaxies drift apart, and all the mass eventually decays into radiation and particles with no mass at all. Photons, particles of light, have no mass. Gravitational waves have no mass. So in the far, far future, mass disappears. The second place where mass disappears is the Big Bang itself. When you go back far enough, the energy levels are so extreme that particles behave as if they have no mass. The distinction between mass and energy breaks down. Penrose's insight is this. If mass disappears at both ends, at the Big Bang and in the remote future, then both ends are described by the same kind of geometry. It's called conformal geometry, a beautiful branch of mathematics that ignores scale entirely. In conformal geometry, big and small are equivalent. Only angles and shapes matter. So Penrose proposes something extraordinary. What if the Big Bang is actually the remote future of a previous universe? What if our universe is just one chapter in an infinite story? A series of eons stretching backwards and forwards forever. In this picture, the previous eon expanded and cooled until all its mass disappeared. Its remote future became a featureless ocean of light and gravitational waves. But within that ocean, there were still structures, massive black holes formed from collapsed galaxies. Over incomprehensible timescales, those black holes slowly evaporated, releasing energy into the void. And eventually, something remarkable happened. Those black holes, the last remnants of the previous eon, drifted together and merged, releasing enormous bursts of gravitational energy. That energy, according to Penrose, survived the transition from one eon to the next. It became the seeds of structure in our universe, the tiny variations in density that would eventually grow into galaxies and galaxy clusters. Our Big Bang was not the beginning. It was a continuation, the aftermath of the previous eon's final events. It's a beautiful idea. But is there any evidence to support it? This is where the story gets truly fascinating. In recent years, astronomers have discovered something strange in the sky, something that shouldn't be there if our standard model of cosmology is correct, something that Penrose's theory predicted, even though he didn't realize it at the time. A young astronomer named Alexia Lopez, working at the University of Central Lancashire, made a remarkable discovery. She found a huge ring in the sky, a structure made up of distant galaxies arranged in a perfect circle. The ring is enormous. It spans more than 1.3 billion light-years across. To put that in perspective, the entire observable universe is about 94 billion light-years across. This ring is a significant fraction of that size, but the size itself isn't the problem. The problem is that the ring is too large to have formed within the standard model of cosmology. According to our current understanding, structures can only grow to a certain size before gravity stops being able to pull them together. The cosmic horizon, the maximum size that any structure can reach within the age of the universe, is about 1.2 billion light-years. This ring is larger than that. The standard model says it shouldn't exist, but it does, and that's not all. Lopez also found a massive arc, a similar structure made up of distant galaxies arranged in a curved line. The arc is even larger than the ring. And more recently, she's found a third structure, confirming that these enormous formations are not flukes or coincidences. They are real. They are out there, and we don't know how they got there. This is where Penrose's theory offers an explanation. In his model, the huge rings and arcs are remnants of the previous eon. They were formed by the gravitational waves released when massive black holes merged in the remote future of the previous universe. Those gravitational waves survived the transition into our eon. They imprinted themselves on the distribution of matter in our universe, creating the rings and arcs we see today. When Penrose heard about Lopez's discovery, he had a reaction that every scientist dreams of. He said, "My God, I should have thought of that." The rings were a prediction of his theory that he had never even considered. It was a retrodiction, an explanation of a discovery made after the fact, but still a powerful validation of the underlying idea. Of course, this is not settled science. There are other explanations for the rings. Some astronomers argue that they might be statistical flukes, random alignments that look meaningful but are actually just coincidences. Others suggest they might be caused by something else entirely, like cosmic strings or other exotic phenomena. But the fact that these rings exist at all is a problem for standard cosmology. They are evidence that something important is missing from our current understanding. Whether that something is Penrose's conformal cyclic cosmology or something else entirely remains to be seen. But the rings are a clue. And in science, clues are the beginning of discovery. Now, let's step back for a moment and think about how physics actually works. Because the story of how scientists discover the universe's deepest secrets is just as fascinating as the secrets themselves. One of the most controversial ideas in modern physics is the role of beauty. Many physicists believe that the laws of nature must be mathematically beautiful. They believe that elegance and simplicity are signs of truth. This belief has driven physics for centuries. It led Einstein to discover general relativity, a theory so beautiful that he knew it had to be right even before the evidence caught up. But this belief can also lead physicists astray. Brian Cox and Roger Penrose have both spoken about this danger. Penrose put it bluntly. He said, "I think this is too often in physics. People think a certain area is very beautiful mathematics, and therefore it's got to be true of the physical world. And there is a big branch in that area. There is string theory. I do mean string theory." String theory is one of the most famous attempts to unify quantum mechanics and gravity. It's an incredibly elegant mathematical framework. It has beauty. It has depth. It has spawned thousands of papers and entire careers. And yet, after decades of effort, it has produced exactly 0 testable predictions. There is no experimental evidence for string theory. There may never be. This doesn't mean string theory is wrong. It might be right. But Penrose's point is that beauty alone is not enough. Nature doesn't owe us beautiful mathematics. The universe is under no obligation to be elegant. It is what it is, and we have to follow the evidence, not our aesthetic preferences. This is a crucial lesson for understanding the nature of scientific discovery. Scientists are human. They fall in love with their ideas. They become attached to beautiful theories. And sometimes that attachment blinds them to the evidence, or to the lack of evidence. The history of science is filled with examples of beautiful theories that turned out to be wrong. The Ptolemaic system, with its elaborate circles within circles, was beautiful in its own way. But it was completely wrong about how the solar system works. So when we hear about new theories of the universe's origins, theories of inflation, multiple universes, extra dimensions, colliding brains, we should remember this lesson. These theories are fascinating. They are grounded in mathematics. They have logical coherence, but they are also speculative. Some of them may be untestable, some of them may be wrong. The best we can do is follow the evidence, and right now, the evidence is pointing in directions we never expected. Let's take a moment to appreciate just how immense the universe really is, because understanding its scale is essential to understanding its origins. The observable universe extends 46 billion light-years in every direction from us. That's the farthest distance that light has had time to travel since the Big Bang. But here's the strange thing about that number. The universe is only 13.8 billion years old. How can we see objects that are 46 billion light-years away? Shouldn't the maximum distance be 13.8 billion light-years? The answer is expansion. The universe has been expanding the entire time the light has been traveling. The objects we see today are much farther away than they were when the light was emitted. The most distant galaxies we can observe are now 47 billion light-years away. The entire observable universe is about 94 billion light-years across. But here's the thing. The observable universe is just the part we can see. It's a bubble in a much larger cosmos. We know the universe is bigger than the observable part because the edges of the observable universe don't look like edges. There's no boundary, no wall, nothing that suggests we've reached the end. The universe continues beyond what we can see, probably much, much farther. How much farther? Some estimates suggest that if the universe is finite, it must be at least 250 times larger than the observable part. But it might be infinite. That's one possibility that current measurements can't rule out. We can estimate this because of what we see in the cosmic microwave background radiation, the oldest light in the universe. This light was released about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. It has been traveling through the cosmos ever since, and we can measure its properties with incredible precision. One of the things we can measure is the curvature of the universe. Is it flat, like a tabletop? Is it curved like a sphere, or curved in the opposite direction, like a saddle? We've made these measurements, and what we find is that the universe is basically flat. Not exactly flat, but extremely close. This is remarkable. A flat universe is unstable. If there's even a tiny deviation from flatness, the universe will eventually curve one way or the other. For it to be flat, after 13.8 billion years, it must have been incredibly flat at the beginning. So flat that it's hard to explain without invoking inflation. Here's how Cox explains it. According to general relativity, the shape of space is determined by the stuff in it. Matter and energy curve space. And what we find is that there is precisely the right amount of stuff in the universe to make it flat, to within about 1 part in 10,000. The most likely explanation, and the one favored by cosmologists, is that the universe is much, much bigger than the part we can see. Think about it like this. If you look at a small patch of a giant sphere, it looks flat. The Earth appears flat from ground level, even though it's curved. If the universe is curved, but we can only see a tiny part of it, it would appear flat to us. So the fact that we measure flatness suggests the universe is enormous, much larger than our observable bubble. And beyond that? Beyond the observable universe? Beyond whatever shape it has? Beyond the limits of what we can ever see? We don't know. We'll probably never know, at least not through observation. Some questions may be permanently beyond the reach of science, but that doesn't stop us from asking them. If the universe had a beginning, will it have an end? And if so, what will that end look like? The current best guess is that the universe will continue expanding forever. This is because of dark energy, a mysterious force that is accelerating the expansion of the universe. Dark energy is the most abundant thing in the cosmos. It makes up about 70% of everything. We don't know what it is, but we can measure its effects, and those effects are pushing the universe apart faster and faster. Before dark energy was discovered, physicists thought the universe's expansion would slow down over time. Gravity is attractive. All the matter in the universe pulls everything together, so naturally the expansion should decelerate. The big question was whether there was enough matter to eventually stop the expansion and pull everything back together in a big crunch, or whether the expansion would continue forever, but slow down asymptotically. But dark energy changed everything. Instead of slowing down, the expansion is speeding up. This means the universe will not recollapse. It will expand forever, faster and faster. Galaxies will drift apart. Stars will burn out. The universe will become cold, dark, and empty. This is called the heat death of the universe. It's not a dramatic end, like a big crunch or a big rip. It's a slow, quiet, and inevitable fade into nothingness. Over incomprehensibly long timescales, stars will stop forming. Existing stars will exhaust their fuel and die. White dwarfs will cool to black. Black holes will slowly evaporate. Eventually, the universe will be nothing but a dilute soup of particles and radiation, all at the same temperature, with no usable energy left for any process. But Penrose's theory offers a different ending, or rather, a different perspective on endings. In his conformal, cyclic cosmology, the heat death is not an ending at all. It is a transition. When the universe has expanded so much that all mass has disappeared, when only massless particles and gravitational waves remain, scale no longer matters. The geometry of the universe becomes conformal. And a conformal universe is indistinguishable from a universe just after the Big Bang. So the heat death becomes the Big Bang of a new eon. One universe ends, another begins. The cycle continues forever, without beginning and without end. It's a beautiful idea. But is it true? We don't know. The rings discovered by Alexia Lopez are suggestive. They hint that something might be connecting our universe to a previous phase. But they are not conclusive. More evidence is needed. More observations, more measurements, more discoveries. And that's what makes cosmology so exciting. We are living in a golden age of discovery. New instruments, new telescopes, and new satellites are revealing the universe in ways our ancestors could never have imagined. We are the first generation to have a detailed picture of the cosmos. We are the first to see the cosmic microwave background radiation with our own eyes, to map the structure of the universe on the largest scales, and to measure the accelerating expansion that will determine our ultimate fate. We might not have all the answers yet, but we are asking the right questions. And with each new discovery, we get a little closer to understanding where we came from and where we are going. If this exploration of the universe's origins has sparked your curiosity, you're not alone. Millions of people around the world are captivated by these questions. And with each new discovery, we get closer to understanding our place in this vast cosmos. Thank you for watching. If you enjoyed this video, please consider subscribing and hitting the notification bell so you don't miss future explorations of the cosmos. And as always, keep looking up, because the universe is still revealing its secrets, one discovery at a time.